Yeah, I wanted to speak about a lot of data which were taken by people, which I just want to sorry. Do you know about this? Ah, they switched off. Sorry. Okay, thanks, Thomas. Yeah. Which I want to acknowledge here. I want to speak about measurements which show that this electrical manipulation of antiferromagnets is possible even if you use quite fast pulses. Very recent measurements actually done in the last couple of weeks by Kamil Olejnik and Vivek Schuler. Also, of course, Pete Wadley. I will show measurements from Pete, XMLD measurements, and some ideas we have. I want to present how to manipulate antiferromagnet maybe in more simple structures, and also considering that it's possible to do it very fast by Pierre Roy and Ruben Otzoa from the Hitachi Cambridge Laboratory. So, I mean, we know obviously all about this spin Hall effect, that this is a way to generate a spin current via a charge current. And the other way to generate spin, net spin polarization is indeed by using the inverse spin galvanic effect in a system where you have a broken inversion symmetry. So the spin Hall effect in principle generates a spin current, but on boundaries of your system you would accumulate spin polarization, which then can diffuse into a system, for example, in an antiferromagnetic system, and can torque the magnetic orientation in this antiferromagnetic system. And here in the Edelstein effect, where you need a broken inversion asymmetry, this can be due to the interface as well. It can occur at the interface as well, but it can also be, in principle, a result of the bulk structure, for example, the crystalline structure of your system, where your band structure is spin split, and because of the steady state redistribution of your states in the Brillouin zone, you get a net polarization, which reflects effectively the polarization of the spin split bands. So this is in principle the idea of people thinking you could use the spin Hall effect as a kind of effective spin injector into also antiferromagnetic systems where the spin accumulation at this interface diffuses inside. And from ferromagnetic spintronics, we know that there are two kind of extreme cases of torques which appear, which have a certain symmetry. One is the so-called field-like term. Here you generate a torque. Here you generate an effective field, an exchange field of your spin polarized carriers with the magnetization, which is typically oriented along the orientation of the incoming spin. So one can understand it intuitively that a spin enters your magnetic system, and then the exchange is so strong that you deface quite. The exchange is strong, and you start processing around the exchange interaction. But on the other hand, you have a certain spin lifetime, and if the spin lifetime is much shorter than this precession time, your steady state solution of this problem is that you actually have only a spin accumulation which has the same polarization than the one you generate via this spin Hall effect in this geometry. But you also can have the other type of spin, which is what is called anti-damping torque, which here you would require a spin lifetime which is much longer, so that the steady state solution is actually dependent on the local magnetization, and so this effective field here depends on the local magnetization. It's perpendicular both to this local magnetization and the injected spin. So it would be, in case of an antiferromagnetic, schematically actually be staggered, this effective anti-damping field. It would be for one sublattice, say in this direction, and for the other sublattice in the opposite direction. So it has this staggered symmetry. We know the field-like term torque to switch shortly back is very inefficient because it acts like an external applied magnetic field. And if you apply an external field to an antiferromagnet, you really have to apply very large fields to manipulate the orientation of the antiferromagnet. You overcome the spin flop field. Typically, these spin orbit torque-related fields are quite small. They are in the micro Tesla or milli Tesla range. So here you will be far from this spin orbit torque. So there will be no possibility to torque an antiferromagnet with a field-like field. However, the anti-damping-like torque might be a way to manipulate, and this was figured out by Helen Gomonnet and also Alan McDonald, where they proposed this kind of torque to manipulate an antiferromagnet in the early wake. However, the problem is also you require very thin antiferromagnetic systems because this all happens at the interface and the spin will be absorbed. So maybe it's better to go back to the other effect where and another problem of the anti-damping torque, sorry, I forgot to mention, is this what was Helen Gomonnet was pointing out in her second lecture on Monday afternoon, that if you have this anti-damping torque, and because it's a function of the magnetization, switching is not really deterministic. You would start to get a kind of precessional motion of your L vector, and then it would depend very crucial when you stop your pulse. And it would also not only depend on the pulse length, it would depend on the damping. So because you have some inertia, your magnetization would start, or your L vector would start to precess further. So you would, in principle, have no way to really deterministic switch the antiferromagnet with this anti-damping torque. So that's why maybe the most interesting way is to look back to these other terms, so the inverse spin galvanic torque in antiferromagnets, which can appear in the bulk, and in particular in system with a broken inversion asymmetry, as I said in the beginning. Here you have a material system which obviously has no broken inversion asymmetry. You have this gold atom here is a center of inversion. However, Thomas pointed out with this great idea that if you consider the sublattices of this manganese to gold, that you have actually locally a broken inversion asymmetry. For example, this manganese atom here has on top of it other manganese atoms and below gold. And here this manganese atom has just the inverted structure, so the gold is on top and the manganese is below. So the inversion asymmetry here is just inverted. So he speaks about inversion partners. And now if you would apply a global current, so the global for the whole structure of your antiferromagnet, you would generate locally now on the magnetic order, this polarization, or an effective field, if you want, which is opposite in sign for the two sublattices. And although the current is absolutely everywhere, the effective field changes on the atomic scale, and this gives you this staggered field, which acts very efficiently on the antiferromagnetic order. And I show you this in the following. That because the field is actually opposite oriented, the torque on the sublattices schematically will act in the same direction. So when the torque, when you switch on your pulse, acts in the same direction, you slightly tilt the moments towards each other, and what happens is an exchange field where then this exchange field, we know it's very strong in antiferromagnetic on a magnetically coupled system in general, then the moments precess around this very fast exchange field. As you can see in this simple macrospin simulation with parameters which are typical for this manganese to gold. So you have a uniaxial anisotropy of a few millitesla, and here the exchange field, the exchange, so the spin orbit torque field, the spin orbit torque field you generate by your current you send through is also just of the order of the anisotropy field, even a bit smaller. And with this field, you can, in principle, very efficiently torque and switch the orientation of this antiferromagnet. So a very small field is applied only, and this field corresponds of current strengths of the order of 10 to the 6, 10 to the 7 ampere per centimeter square. So something which is really feasible. Since this spin orbit field, as you can see here, which you generate, the staggered spin orbit field has a Rashba symmetry. It means that depends on the current direction where this spin orbit field interacts with your moments. It is important if you have a biaxial system that you are able to switch the magnetization, or the L vector, if you want, by 90 degrees. So you have also to apply the current by 90 degrees when you want to switch it back. So you go in principle to a structure which has this cross geometry. Right? You can send the current from here to here and from here to here. And if you send the current along one direction, say this is our x direction, the field will be along the y direction. So if the moments are along the x direction, if your L vector is along the x direction, you will torque it in the way that it will switch eventually to the y direction. And if you want to switch it back, you have to send the current from this direction back to this direction. This is what you naively would think is a requirement. And indeed, experiments then later I will show have shown that exactly this cross structure was used to first show the switching of the antiferromagnet in such a structure. And if you do so, if you use now a kind of micromagnetic, or actually it's atomistic spin dynamic calculation in such a square of 150 times 150 times 5 such unit cells, one can see if one applies a current along one particular direction, say your L vector is along x, so the current is along x, you switch it after a very, very short time towards y, and then sending other pulse of the same length along y, you can switch it back that the L vector is along x. And if you look to the magnetization which occurs, indeed, you start for a very short time tilting the two sublattices now in z direction, which create this exchange field that the moments can torque around. Interestingly is because it's a field-like torque, so the torque is not depending on, or the effective field is not depending on the orientation of your magnetic moments. It's a very robust way of switching. As we know, antiferromagnets, if the L vector changes, there is some inertia related to it. And so if you have a very low Gilbert damping, for example, in this system, and you switch at very high spin orbit fields, there is a small chance of overshooting. But if at a slightly higher Gilbert damping, the switching is very deterministic, because if it has, in principle, switched by 90 degrees, there is no torque anymore, and the system is, in principle, in its lowest energy state. However, I want to show you also that you don't necessarily require a 4-terminal device to switch, but it's also, in principle, possible with a 2-terminal device. And of course, one can say we have this precessional kind of precession, but if the pulse is really well tuned, then you should be able to just overcome one of those maximas, the anisotropy maximas, which are along these red lines here, and you can switch your L vector from this direction to this direction. So say current direction dependent means it would switch either clockwise or it would switch anti-clockwise. So saying you send a current in a direction that it switches clockwise, you would be able to switch it if the current pulse is very short, in principle, between these two axes. This, however, is quite difficult, I imagine, and as I said, also you have the inertia of this system, so you may overshoot as well. It's where you would have to tune the system very well. However, what you can do, you can go into a uniaxial system. So a uniaxial system would have only one energy barrier along this direction, and now again you rotate your current direction 45 degrees to this uniaxial orientation here. And this makes it possible, again, to switch. If you switch clockwise, you will overcome the energy barrier. If you switch anti-clockwise, you don't overcome the barrier. So you can switch with one current direction from this direction to the opposite direction. So you would rotate by 180 degrees your structure. And sending the current in the other direction, you can switch it back. This makes it much more interesting for application because you have now a way, not using a 4-terminal device, but using a 2-terminal device. The problem is how you distinguish, by measurement, an L vector, which is either like this, or the magnetization is like this, or it's like this. So this is obviously another thing, and we have ideas actually also to distinguish by transport measurements such a configuration. But I don't want to go at the moment too much into this. I wanted just to say it is a way you can actually uniaxial antiferromagnets might be even more easier to manipulate from the device design point of view. And another interesting way to, of course, manipulate an antiferromagnet, a uniaxial antiferromagnet we just heard in the first talk this morning, is you can use actually domain wall motion. And in Stuart Parking's experiments, what he has two ferromagnetic layers which are exchange coupled to each other. And the domain wall, as he explained, is mostly driven by the exchange between these two, the exchange torque when he starts to send a current. And the same thing actually happens in this manganese to gold, and if it has a uniaxial anisotropy. You can consider this manganese to gold as having actually, these are basal planes of ferromagnetic order which are antiferromagnetically coupled. And very similarly, a domain wall here would move now at very, very high speed if you excite it with a current. Interestingly, when it starts to accelerate, it emits spin waves to one side, but look to the velocity you can achieve. This was also pointed out in a very nice lecture by Alan Galvanic, that those domain walls move with very high speed, and moreover, what they also show, it's that this motion can be described by a Lorentz invariant thing. And one result of this Lorentz invariance of this motion is that you reduce the domain wall width to get a kind of length contraction if you reach a critical velocity. And as you can see in the simulation, we started with a much wider domain wall in a steady state situation, and it becomes then very narrow when it accelerates and reaches its steady state velocity. What also Alan actually pointed out is that in antiferromagnetic system, the Walker breakdown, the stability is not such an issue. So things like Walker breakdown, where the domain wall structure becomes unstable because you overcome a principal energy threshold, which is defined by the anisotropy of your system, typically the demagnetization field in the system. This is not the case here. Here you are actually stabilized by the exchange field. And your spin-orbit field, which drives this domain wall motion, should become larger or of the order of the exchange field in order to reach such a kind of Walker instability, which obviously you don't do. Before you reach a velocity threshold, as you can see here, which is actually determined by the group velocity of the spin waves or of the magnons in this particular system. And these are now parameters from this manganese to gold, which are experimentally obtained. And from those parameters, you would expect a velocity, a maximum velocity of the order of 45 kilometers per second. So very, very fast because exchange torque-driven domain wall motion. So this makes it very interesting to look into systems, how you can actually switch antiferromagnetic system fast. And so the real system where we do the experiments is not the manganese to gold for different reasons. Maybe one reason is that the anisotropy in the system is quite strong and this switching is not so easy to observe there. However, it has been observed in a different material system. Pete has given a very nice talk about this, about copper manganese arsenide, where you also have this inversion partners, because the broken inversion asymmetry generates you spin accumulation at your manganese atoms, which has opposite orientation for the two sublattices and give you this staggered field-like torque. You can have a uniaxial, indeed, copper manganese arsenide, and this makes our domain wall idea and domain wall propagation in the system very probable as an experimental setup, because what you see here, it's a particular copper manganese arsenide structure grown by Richard Champagne in Nottingham, and the picture was done by Pete Wadley, XMLD measurements, and they show you this very extended long black lines, which always, if you see a full line, they always go around an area which actually corresponds to a domain. So you cannot, by XMLD, you cannot distinguish 180-degree rotation, so the contrast from this domain and this domain is the same. However, you can see the range where the magnetization is rotating, so a domain wall. The size of the domain wall, interestingly, in this material seems to be of the order of about 100, 200 nanometers, so quite large extension, maybe because of a weak anisotropy in the system, but something which is maybe very easy to access experimentally. However, we know they move very fast, so we have to think about ways to switch them very fast. Just going a bit further to this copper manganese arsenide, this material is typically grown on a 3,5 substrate, in this case a gallium phosphide. It's indeed an antiferromagnet. And now exploiting this biaxial anisotropy and the fact that we have the kind of Rashba type of spin orbit torque, one makes this kind of cross-like structure, sending current pulses either along this direction, which is along one of the easy axes, or along this direction, which is along one of the other easy axes. And those other 45-degree rotated cross structure here was used to read the information by a transverse AMR. So the symmetry of the transverse AMR would enable you if the L vector is along the black line or if it's along the Y line, and you have to drive a current, say, along this arm here, then you can measure a voltage difference, or you measure a resistance, a transverse resistance along this orientation. So this has shown this, these experiments have given these very, very nice results. As you can see here, as you see also is it's obviously not after one pulse, it's not saturated at all. So if you send a second pulse, there is still a variation of your signal and further on, and then you can switch backwards. And you repeat the experiment with the same kind of sets of pulses, and you can repeat this quite often, but it shows you, first of all, it's an incomplete switching, and Pete has shown these very nice pictures that when you look in the XMLD doing the switching process, you only switch a part of those kind of domain structures. It's not all, doesn't become white and black, but just parts of it becomes black and part of it becomes white. It's quite a complex switching. But those reproducibility of those say intermediate states might be interesting for some application, and there will be a talk by Xavi Marti this afternoon, where he speaks about ideas to exploit those kind of metastable, or not metastable, they are stable states, but incomplete switchings. For example, you can think this device has a kind of memristor functionality, or use it as counters, etc. So this might be quite interesting for application. What's also interesting is it's another feature of antiferromagnets that they are in principle robust against magnetic fields. So what we did here, we were switching the antiferromagnet at 0 field and then applying a very strong field up to 12 Tesla. And as you can see here, there are two possibilities. If you have the field now along your orientation of your pulse, this means the field is actually perpendicular to the switched moments, the moments you have switched with your pulse, because you have this Rashba symmetry of this spin orbit field. It means you have a field where you now start to tilt for those which are now perpendicular to this applied field, to tilt the sublattice to each other. And by tilting it, you get a Zeeman energy gain in the system. So domains which are along this, this orientation of the applied field, they are energetically more favorable than domains which are actually parallel to it. Yeah? So you can see for the case where you have switched the, where the magnetization is along the current direction, hence where the magnetic field is perpendicular to the switched magnetization direction, these states get further apart. The signal increases with increasing field. You don't erase it, you increase it in this case. And if it's the other way around, if you actually promote with the magnetic field domains which are not, which have switched in the parallel orientation, then those domains seem to be less important, maybe become smaller, and the signal decreases at about 12 Tesla. But for some reason we don't understand, it's a kind of elastic process. So if you remove the magnetic field, again you recover the original states. So this is, from the application point of view, interesting. You can apply really strong fields. You don't do anything to your magnetic states in principle. But you even can switch at a field of 12 Tesla. So if you apply a field of 12 Tesla, you apply effectively quite small current pulses, and you can still switch your magnetic order. And this is unprecedented in any ferromagnetic system, of course, that you can apply a current pulse and you switch the magnetic order. The strong magnetic field will couple much, much stronger to your magnetization, and you will be unable to manipulate with a spin transfer torque or something like this, a magnetic structure. So I was saying the idea of this talk is maybe to go towards fast switching, and to fast switching one has to go to smaller devices just because the Joule heating becomes smaller if you want to switch at the same current density. So a way to make devices smaller is to go to a more simplified device structure. So those crosses used now are not anymore these double crosses where you use one pair of crosses for writing and the other pair of crosses for reading, but you use now one cross for both writing and reading and apply a current in such a way that you use two arms simultaneously, that the current lines are either perpendicular to the moments or parallel to the moment, or always perpendicular to the moments you want to switch, but that they actually combine within this stripe overlap in this cross central area. You have in principle current lines which are 45-degree rotated to your cross structure. And on the other hand, you can then use the cross structure itself as the detector by having this 45-degree rotated arrangement to be able to measure the transverse AMR. And though the first devices were this, what I showed you in the beginning, were devices of the order of 30 micrometer. Those devices are of the order of 2 micrometer. And indeed, in those devices, it's now possible to switch already at a current density, at the speed of pulses of 3 nanoseconds. So you can switch reliably between two states having only 3 nanosecond pulses. As you can see, current density indeed increased. You have to have larger pulses. And then let's see what actually are the requirements for the current density. So if you have very long pulses, this, what is plotted here is in principle 1 over the pulse length as the required current density you need in order to switch your copper manganese arsenide. And as you see, you're in a region where probably thermal activation plays a big role. So you get this nonlinear behavior in the beginning. And then you more or less follow a straight line. With increasing current density, you can go to shorter pulses, which make it as possible to flip. And here, this is again, this measurements done with pulses of the order of 50 milliseconds where you can switch between the states. But I showed you those data. Here you have 3 nanoseconds, and very new data from Carmine show you can actually switch even with 280 picosecond. So obviously, there seems to be no limitation to the switching speed if you follow this line, this increase of current densities up to a speed of 280 up to 200 or 300 picoseconds, which is in a sense amazing because it's still the first material which is used in order to do a spin orbit torque switching. So, but if you want just to continue maybe thinking, in the beginning I said the switching should happening on an even much shorter time scale, either by domain wall motion or by coherent switching, so on a scale of the order of picoseconds. So if we go, for example, to pulses where one would expect a rotation of the 10 picoseconds, we would require current densities which are quite high, so 10 to the 9 ampere per centimeter square. It's maybe not easy to generate for such a short time scale. An idea we have, and what we are now doing actually, are the implementation of those photoelectric switches, those so-called Austin switches. So here is an example of a conventional Austin switch where you have typically grown on a low temperature grown gallium arsenide substrate. You have 2 conductive paths, which is typically a metal, and you have an area between them. And if you shine light on it, you, for a short time, the time of the lifetime of your carriers, you generate charge carriers, and you actually short this line, this current line, and current can flow from the right to the left. If you apply a large potential between the two parts and shine light on it, you can in principle generate quite a quick current pulse, and probably also a strong current pulse. We have designed a little bit a different way because we want to make use of the fact that our copper manganese arsenide grows on this 3,5 structure, on the gallium arsenide or on gallium phosphide. So what you can do is you can in principle design in the substrate, in your wafer, already an embedded PIN junction, which has a P region, intrinsic region, which is used to absorb photons, which come from a femtosecond laser, for example, and a top layer where we have n-doped gallium arsenide to pin the Fermi level towards this metal layer. In this case, it's copper manganese arsenide. With such a structure, you can, in principle, apply quite large biases and to use the optical pulses, femtosecond pulses, which might be even spin circular polarized. You could, in principle, exploit the fact that you generate spin polarized optically, spin polarized carriers, and you would have such a kind of pulse. This is what you would expect. Your very sharp rise time, which depends on the time of flight of your electrons you generate between the generation and your electrodes, and then a decay which depends on the geometry of your device. In a sense, it's a capacity which drives you the length of the pulse. But as I was showing you in the beginning, it's not so important to have a very long pulse because our switching is robust. What's important is that the rise time is very fast. And as I will show you in our measurements here, we achieve rise times which are well below 1 picosecond. So we can have very, very sharp pulses with such a system. So this is now a real device, but containing unfortunately not copper manganese arsenide, containing only iron, a thin iron layer, because we wanted to see the effect of spin polarized high intense currents on a thin iron layer. And what you see in darkness, you have this nice diode behavior. You can apply quite large fields. You generate a very large electric field in this. And then if you shine light on it, obviously you will generate a photocurrent. And OK, I will go quite quickly. And by doing some pulse correlation measurement, you can actually identify the pulse, the current pulse you generate, which is of the order of smaller than a picosecond in rise time, and the fall time is given by the geometry of the system. And if you look about the intensity of the current you generate, the intensity is of the order of actually what we would require for those short pulses if we would be able to bring this current into our copper manganese arsenide in a thin film of copper manganese arsenide. This, of course, makes it now, it's a very different approach from optical excitation as we heard before. Normally, people think about demagnetization of your magnetic material and getting then fast switching due to this demagnetization, to the exchange and exchange field. Here we use the spin orbit field, which we apply for a very short time. We translate this femtosecond pulse into a picosecond current pulse and hope to be able to manipulate this. The way of detection could be also done optically, so one can think about pump probe experiments. There is a poster by Peter Nemetz and Wiet Seitel. They measure the linear dichroism optically of copper manganese arsenide and identify this as a time-dependent signal, actually. And so it is possible to apply, in principle, this approach, this fast diode approach, with this with the magneto-optical response detection of the linear dichroism. So yes, and in principle, you can also even combine this with an electrical measurement after this, which would be a static measurement, just to see have I switched or have I not switched. So those three things can be combined in one experiment, and this is what we are now doing in future, or soon, hopefully. So just to conclude this part of my talk, there is what I showed you. It's very efficient to switch an antiferromagnet of a special symmetry with the staggered spin orbit torque field electrically. It's robust and deterministic. And one can even identify device structures where you can make it much more simpler. You don't require a cross geometry. And domain walls are maybe extreme interesting systems in those antiferromagnetic systems because they move at very high speed. You don't have things like Walker breakdowns to worry about. And yeah, the experiment, it's in principle possible we could do ultra-fast switching with optical excitation. Thank you very much.
Questions? So I have a minimal question. So what is the second part of the talk which we missed?
The second part of the talk was about the
nice.
the anti-damping torque on an antiferromagnet, where we actually, there comes another question, I maybe can, where we try to actually, or where we show that it's in principle possible to torque iridium manganese, the system which was also shown by Stuart Parking, by using the anti-damping spin-orbit torque.
The non-collinear one, or?
The non-collinear one, yeah.
Does it work?
Yes.
In principle,
in practice. So should I talk about this? Okay, maybe I'll talk about this. No?
There is a question.
Can you show something on the equilibrium discrimination between the 180 degree domains?
Okay, how you measure the identify the resistance. Because AMR, which is always also linear dichroism, would be in principle independent if you switch by 180 degrees, so you would have the same signal for after 180 degree rotation of your electron. However, again, you can use this kind of device geometry, where your easy axes are rotated by an angle, say by 45 degrees in this case. And because of the spin orbit torque field, which is stacked, which acts very nicely on your L vector in a way that it goes either clockwise or anti-clockwise. Now after switching, you can use, for example, a small reading coin, and you will see for one direction, you actually rotate your L vector towards the perpendicular direction, which gives you rise to an increase of anisotropic magnetic resistance effect, or in the opposite current direction, or it would go in the other way. Or alternatively, if you just keep one current direction, for one L vector it would go clockwise, and for the returned L vector it would go anti-clockwise. So it would in one case, well not anti-well, it would in one case it would move towards your bar, you would reduce, in the other case you would increase. And this is something we are actually measuring at the moment. And there are some first results, but I can't show it at the moment because it's not totally complete, but it's possible. This is a detection of 180 degree rotation.
So let's think. Yeah, I think that.
That's a quick question. I just want to be interested in what is the science of the anti-ferromagnetic domain walls in these systems?
Pardon?
You mentioned the motion of domain walls.
Yeah.
And I just wondered what is the width of the domain walls?
The width is determined very similar like in ferromagnetic system by the anisotropy and by the exchange. So in this case, the width measured in this relatively weak anisotropic copper manganese arsenide is of the order of 100 to 200 nanometer. Somewhere in the picture from here. So if you make a scan over the contrast in this XMLD, you see the width of the domain wall is of the order of about 200 nanometer. But in more stronger systems like this manganese 2 gold, which has stronger anisotropy, which is measured, here the width you would expect, it's not detected, it's just expect, and therefore it's shown here, is of the order of actually also of the order of about 100 nanometer. So it's rather wide, but it would depend on the anisotropy. If stronger anisotropy would make the domain wall more.
The domain walls are relatively big.
Yeah. You mean the dimension of the domain walls?
The width of the domain
the width of the domain wall.
is very wide.
In this case, they're very wide, but it's like if you have a system like parallel in-plane, you have very wide domain walls, as you mentioned, but you can have, if you have an antiferromagnet with much stronger anisotropy, you would have corresponding with the domain walls much more narrow.
Which systems would you imagine?
Okay. I think we can proceed a bit. So thanks once again to